In this episode, we are going to build an RNN to translate from English to Italian. We are going to be basing the majority of this model on what was discussed in the 2013 paper by Ilya Sutskever. So essentially, we will build this encoder decoder architecture. I've taken an example dataset of sentences from Kaggle. These are English to Italian sentences, and you can download it from my GitHub account. Now, what I have done here, if we take a quick look, I've essentially reduced the source vocabulary, so the English vocabulary, so that we have around 5,000 different words, and this is going to make it easier for our smaller network to train and to actually learn something. So the vocabulary has sentences in English on one side, then it's got this kind of arrow separator, and then the sentence in Italian. And as you go down, you can see that sentences become longer and more complex. So here I've got some code to read the file in memory and to process it. We have in total 120,746 sentence pairs. And as we did when we built a basic language model, here we need to tokenize all of these sentences. And of course, we need to build a vocabulary. Just in this case, we're going to have two vocabularies, one for the English language and one for the Italian language. And you can see the helper functions here, very similar to what we did before. So I'm not going to spend time, but you can see that we end up with our two vocabularies, and we have roughly 5,000 words in the Italian vocabulary and 13,000 words in the English vocabulary. Sorry, obviously the other way round. And this is an example of how we can use this. We can pass an English sentence, who are you? And we can convert that sentence essentially into a tensor where each word is replaced by the index in the vocabulary. And we can also do the other thing. We can pass a tensor in, as we do here, and then we get the corresponding words out. Now, we also need to build datasets and DataLoaders to work with PyTorch. And as we're doing this, we are going to add some special tokens to our dataset. We're going to need a padding token. Sorry, I didn't mean to double click. So the padding token is useful because we're going to put our sentences into batches. We're going to sample randomly from the dataset, which means that a batch will have sentences of different lengths. But obviously, we need them to be the same length. So we're going to use that special token to pad out shorter sentences. And then we have the end of string and start of string tokens, and also the unknown word token. We don't really use it in this particular model, but I just added it there for reference. So this code is simply going to update the dictionaries to add these special tokens. Here is our standard dataset that we built by extending PyTorch dataset object. And obviously, this is going to return the pairs as tensors. So it's going to return the English tensor and the Italian tensor. The only thing that I've added here, which is worth mentioning, is the collate function. So we did say that we are going to need to pad sentences out, and indeed, we create a collate function that we can give PyTorch so that it knows how to pad sentences out. And in this particular case, we're telling it to pad sentences exactly with this special token that we have provided. So we can then create the DataLoader from the translation dataset. And again, we pass the collate function, shuffle to true because we want to sample randomly when we create a batch. And we set the batch size to 64. And we end up with around 2000 batches, which is not that bad. And we can take a look at the first batch. So again, this contains 64 tensors, which are English sentences, and then the Italian translations. And you will notice immediately that we have a lot of zeros towards the end, because indeed these sentences have been padded. We are now ready to implement the encoder-decoder architecture, and we are gonna implement the encoder and the decoder separately. So the encoder simply takes the input, which is the vocabulary size, and projects it into embeddings. So this is basically what we're doing here. And then it takes the embedding or embedded inputs and passes them to a recurrent layer. This is an LSTM cell, which then projects them or expands them into the hidden state with whatever number of layers we're passing here. By default, we are going to use one layer. And as usually, we've got batch first. And this is the forward pass. Now you'll notice that in the forward pass, the first thing that we do is actually reversing the input sentence. And this is something that empirically they found out while they were doing this work, that improves the, let me see. Oh, there it is. We found that reversing the order of the words in all source sentences, but not target sentences, improves the LSTM's performance. So that's why we're doing this here. We do the embedding, we pass the embedded inputs to the LSTM layer, and we get the outputs and the hidden and self states. Then we have the decoder. So the decoder is going to have its own embedding with the vocabulary size. This is going to be the vocabulary size of the Italian language, because that's what we're translating into. And then it's going to pass all of these to the LSTM cell, pretty much the same as before, but we are adding a fully connected linear layer at the end, which is going to take the output of the LSTM cells and project it or translate it into the vocabulary size, so that it becomes a probability distribution of the next token. And again, this is identical to the language model we did before. And you can check the forward pass yourself. So now we're going to implement or instantiate this encoder and decoder. These are the hyperparameters that we are using, 256 for the embedding size, and the hidden size is going to be 512. We are keeping these sizes the same for the encoder and the decoder. They could be different if we wanted, but it's much easier to keep them the same. So we're now ready to see how inference works. This is quite simple. We have an input sentence in English. We put each word through the decoder until we get to the last word. We take the last hidden state and self state, and we use those for the decoder. So we feed them as the initial states in the decoder. We feed the start of sentence token in, and then we sample from the output the most probable word. We're going to use a greedy approach here. We feed it back in, and so on until we get the end of sentence token. So that's essentially what this translate method is implementing here. I will not go too much into the description. You can check it out yourself. Now that we've implemented the method, we can try to translate a sentence. Maybe just this: Tom likes listening to music. Maybe that makes more sense. And as you can see, obviously we haven't trained the model, so we just get random words out of it. These words mean absolutely nothing. And you will notice that the only thing that's worth looking at here is that we're passing a max length, because what happens if the decoder doesn't produce an end of sentence token? We don't want to go on forever, so we give it a maximum length and so we stop there. So either we stop at the end of sentence token, or we stop when we reach the maximum length. And indeed, if you were to count all of these, you would see that these are just 15 random words. Now we want to train this model, and training is actually quite simple in spite of all of the text which is on the screen. What we're going to do, we're going to pass one batch through the decoder. We're going to take the hidden state, pass it to the decoder. Sorry, I meant encoder here. And so this is the decoder. And then we pass the start of sentence. We produce the first set of predictions for the next token. And now we then use teacher forcing. So instead of sampling from here and inputting this into the model, we are actually going to go into the ground truth and take the first correct token for that translation and feed it into the next step of the RNN. So this allows us, again, to force the ground truth to the model, which is going to learn a lot faster. But as we said, there are some disadvantages here because the model can be biased, always expecting the correct word next. So what you find when you try to train larger models is that teacher forcing ends up with a model which is very good at producing sensible words in the target language, but sometimes these words and sentences are not very well related to the input sentence. But we'll take a look at that in a bit. Also here we are using Adam instead of stochastic gradient descent. Now we did discuss Adam. It does combine momentum and RMS prop, and it will make this training converge much faster. But we are also using Adam with a W. W stands for weight decay, and this is essentially L2 regularization. We did discuss that in our evaluation episode, but we're basically going to add a penalty for very large weights. So this is good to make the model generalize very well, and it makes the process much more stable, especially when we train very deep neural networks like this one. So that's the training loop. We use cross-entropy loss, but we add an index to ignore, which is the padding token. We don't want the cross-entropy loss function to spend a lot of time looking at this padding. It's not something we want the model, or we need the model to learn, so we can tell it to skip that when it computes the loss. Then here we have two optimizers, again Adam W for the encoder and the decoder parameters. We're gonna train these for 10 epochs, so we set both of them to train. We go through each epoch, and the forward path is and the training loop is pretty much the same as all the other training loops we have seen. We take the batched input sentences, we pass them through the encoder, we collect the last hidden and self states for all of the sentences that we've inputted in the encoder, and these become the decoder hidden state and self state, which we're going to pass through the decoder here. And we also start the decoder with the start of sentence token, because as you can see up here, we need to provide the first token to the decoder. So we're going to do this for the length of the sentences in the batch. So we do this one at a time. We get the logits. So logits are these ones at each step. And then we compute the loss. And as you can see, we then use teacher forcing, because the next input that we're going to pass into the decoder is actually going to be from the target tensor rather than being from the logits that we generated. And again, this is teacher forcing. If you want it to be a little bit more sophisticated, you could add a teacher forcing rate or probability. So you could tell the training loop to only do teacher forcing 80% of the time, so 50% of the times. And instead, the remainder of the times, you can actually feed it whatever prediction makes sense from your logics. So you can experiment with this. The other thing that I have commented out here, we are calculating the loss across all of the produced outputs and the entire sentence. You could also pick just one or a subset of these tokens that have been produced or these predictions that have been made and only compute the loss on those. This acts as another form of regularization to prevent the model from overfitting. So we can now run this training loop, and it is going to take a little bit of time, so I am going to see you in around 10 minutes. So this is now finished training, and as you can see, the loss was steadily going down. Probably if we left it to train for a little bit longer, I think the loss would have come down even more. But let's take a look at how this model performs on our previous sentence. So we've got here Tom likes listening to music, and we had random words before. Let's see what the model gives us now. A Tom piace ascoltare la musica. This is a perfect translation of that sentence in Italian. Let's try to spice it up a little bit. Maybe we can say she likes listening to music. Le piace ascoltare la musica. This is a perfect sentence. I've got here some other sentences that we can try. They're pretty short, but they should be translated correctly. Tom ha detto che sarebbe venuto. Another very good sentence. Actually, this is wrong because it's not come, but in this case, it doesn't pick the not. So the sentence, that's the correct translation for this. We can try other things such as maybe he is a good teacher, è un bravo insegnante, and then we can change this to she is a good teacher. Reason why I'm doing this is because I want to check if the model has learned the rule of gender in Italian, where she would require the final O to become an A, because it's obviously the feminine version, and it has not actually learned that. So this should be brava, but it is bravo. So obviously the model needs to be trained a little bit longer or with a longer or larger data set. Let us try a final word. She likes drinking hot chocolate. That's slightly more complex. And again, this makes absolutely no sense. Or better, this is what I was saying before with teacher forcing. Le piace bere il giorno dopo means she likes to drink the day after. So il giorno dopo has got absolutely nothing to do with hot chocolate. But this is a little bit of an artifact of that teacher forcing and not training the model enough, or maybe not having enough data in our very small data set. Let's see if it can translate she likes chocolate. Le piace la cioccolata. So this one, it is translating correctly. I wanted to quickly show you the other improvement we can do to this model, which is creating a bi-directional RNN. A bi-directional RNN is a very simple concept. It is the same RNN, but we simply run the input in one direction and then we run the input in the other direction. And so we end up with two final states, two final cells, and all of the outputs at each state duplicated, and we can just concatenate these together into one final hidden state and pass it to the decoder. And the idea is that because we are processing the sentence in both directions, the final state, it's going to capture more of the context and it should perform better. Now, practically, this is very simple to implement. We set bi-directional to true, and it does it for us. And then here I have a little bit of PyTorch Kung Fu to essentially concatenate the outputs here together so that we return them as one single output state, or one single hidden state and one single cell state. If you want to look a little bit into the details, whenever you have a bi-directional RNN, what's happening here is that you have a dimension, the first dimension of the hidden state and the first dimension of the cell state essentially contains the 0 is the direction going forward, so the standard one, and 1 is the hidden states for the direction going backward. So here I'm simply extracting these and concatenating them together. And then obviously the decoder is essentially the same. What changes is the way we initialize the decoder, because now the hidden size that the decoder receives is twice as much as the hidden size of the encoder, because again, we are putting these the forward and backward paths of the bidirectional RNN together into one single hidden state. So I'm going to go and instantiate this, and I am going to run another training loop. Maybe, again, if we try to translate a sentence, again, we get 15 random words, and now we can reuse this training loop over here, and let's see if 10 epochs are enough for this model to do a little bit better. So we've now finished the 10 epochs of training for the bidirectional model. Let's take a look at how it performs. But again, because the loss was still going down, it's probably worth training this for at least 15 or 20 epochs if you want to get some better performances. But anyway, let's see how the model does. She likes chocolate, le piacciono le sue cose. This is even worse than before. Le sue cose means her things. So it didn't work that well. I think this needs to be trained a little bit longer. Let's see. Okay. Tom likes chocolate. It does understand this. A Tom piace la cioccolata. That's perfect. Let's try. A Tom piace la cioccolata calda. That's a correct translation. Let's see if this one is translated correctly this time. If you remember from before, not wasn't being translated correctly. Let's see what this is doing now. Tom ha detto che non sarebbe venuto. That's a perfect translation. I will not bore you with more of these Italian sentences, but clearly the model is starting to work and it needs to be trained longer on a larger data set. One of the things that we can also take a look at, which might be interesting, is comparing our model to the model used in this paper. And I think they've got some details towards the end. Let us check. What was the size of their model? So they have 4 layers instead of just 1 layer in the LSTM cells. Each layer has 1,000 hidden units, and the embeddings were 1,000 dimensional word embeddings. So our embeddings are 256. Our hidden size is half of their hidden size, and we only have 1 layer. The other parameter which is interesting, the vocabulary size. I think they have an input vocabulary, which I think is in English, of 160,000 words. Our English vocabulary is 5,000 words, and an output vocabulary of 80,000 words in French. Something else, the size of the model, 64 megabytes of recurrent connections and 380 megabytes in total. Something else which is interesting, they did use stochastic gradient descent. We used Adam, so they didn't use momentum. They started with a pretty high learning rate, and then they started having that rate every half epoch, and they trained their model for 7.5 epochs. And their batch size was 128, whereas our batch size was 64. So this gives you an idea of the difference between our sample model and what they actually did in this paper.